Storms are becoming stronger. Wildfires are burning for longer periods. Droughts are spreading across once fertile regions, while destructive floods are hitting towns with almost no warning. These events may look separate, but scientists believe they are connected to one major change taking place across the planet. Earth is getting warmer. The disturbing question is not simply how hot the planet will become. The real question is whether this warming could push Earth into a completely different climate state. A state in which forests disappear, coastlines change, animals struggle to survive, and some regions become too dangerous for human life. Scientists sometimes describe such a world as a hothouse Earth. This idea may sound like science fiction, but our planet has experienced extreme greenhouse conditions before. Millions of years ago, global temperatures suddenly increased. Tropical forests moved into new regions. Oceans lost oxygen. Wildfires became more common, and many animals were forced to change their bodies just to survive. Today, researchers are studying that ancient event because it may offer a warning about our own future. Could history be starting to repeat itself? And would modern life be able to survive the transformation? To understand what may happen next, scientists are looking deep into Earth's past. One of the best places to search for answers is the Bighorn Basin in the American state of Wyoming. Today, this region looks dry, empty, and almost lifeless. Rocky hills stretch across the landscape. The soil is dusty, the vegetation is limited, and the summer sun can be unforgiving. But this barren land contains a remarkable record of a very different world. Buried inside its rocks are fossils from approximately 56 million years ago. At that time, Earth experienced one of the fastest natural warming events ever discovered in the geological record. Scientists call it the Paleocene-Eocene thermal maximum, usually shortened to the PETM. During this period, enormous amounts of carbon entered the atmosphere. Researchers are still debating exactly where all the carbon came from. Powerful volcanic activity may have played a major role. Methane released from the ocean floor may also have added to the crisis. Whatever the source, the result was dramatic. Global temperatures rose by around 5 degrees Celsius. That may not sound enormous, but an average global increase of 5 degrees can completely transform the planet. The oceans became warmer. In some places, oxygen levels dropped. Ocean chemistry changed, ecosystems were disturbed, and entire climate zones began to move. There was little or no permanent ice at the poles. Warm forests grew in regions that are frozen today. Animals and plants were forced to migrate, adapt, or disappear. The PETM lasted for thousands of years, but the most important detail is the speed at which the warming began. In geological terms, it happened very quickly. That is why scientists are so interested in it today. The modern world is also experiencing a rapid increase in greenhouse gases. However, there is a frightening difference. Humans are now releasing carbon into the atmosphere far faster than natural processes released it during many ancient warming events. The PETM may therefore show us the direction in which the planet could move, but modern change may happen too quickly for many species to follow. Paleontologists working in Wyoming carefully search the exposed rock layers for fossils. The work is slow and difficult. A researcher may spend an entire day under the hot sun and find only one small tooth or a broken piece of bone. But every discovery adds another piece to the story. One of the most surprising findings from the PETM involves the size of mammals. Scientists discovered jawbones belonging to an extinct plant-eating animal. The fossils came from 3 different periods: before the warming, during the warming, and after temperatures began to fall. The animals living before and after the extreme heat were noticeably larger. The animals living during the hottest period were much smaller. This was not simply because the fossils belonged to younger animals. The teeth showed that they were adults. Their entire species had reduced in size. Other mammals showed a similar pattern. Early relatives of modern horses also became smaller during the PETM. In some cases, body size decreased by nearly 1/3. Scientists call this process dwarfing. Why would a warmer world create smaller animals? Smaller bodies release heat more easily than larger bodies. In a hotter climate, this can be an advantage. Small animals also require less food and water. If vegetation becomes limited or less nutritious, a smaller body may be easier to support. Animals with shorter generation times may also adapt more quickly because useful traits can spread through a population faster. During the PETM, plants changed dramatically. The forests that had once covered Wyoming did not remain the same. As temperatures increased and rainfall patterns changed, many local species disappeared from the region. Plants from warmer areas moved north. The landscape became drier and more open. For plant-eating animals, this meant that their food supply changed both in quantity and quality. Dwarfing may have been one of the ways mammals survived. Could modern animals experience a similar transformation? Researchers in South Africa are already investigating a possible example. The Kalahari is one of the hottest and driest environments on Earth. Temperatures can rise to dangerous levels, and rainfall is unpredictable. Yet many animals have learned to survive there. Among the best-known residents are meerkats. For decades, scientists have followed wild meerkat groups, recording their behavior, reproduction, movement, body weight, and survival. Because these animals have become familiar with the research teams, scientists can approach them closely and collect information that would normally be impossible to obtain from wild mammals. The long-term records have revealed an important pattern. On extremely hot days, young meerkats gain less weight. Over time, researchers have also noticed that 3-month-old meerkats have gradually become lighter. At first, scientists suspected that the adults might be finding less food during periods of intense heat. But observations showed that the amount of food did not decrease enough to explain the change. The food itself may contain less moisture during hot conditions. Young animals may also use more water and energy to keep their bodies cool. The meerkats may not yet be evolving into a permanently smaller form. True genetic adaptation can require many generations. Still, the trend shows how quickly heat can influence growth and development. The biggest danger is not simply that the climate is changing. Climate has always changed throughout Earth's history. In ancient times, a major climate transition could unfold over thousands or even millions of years. Species had time to migrate slowly, reproduce, and develop new survival strategies. Modern warming is taking place over decades. For animals with long lives and slow reproduction, that may not be enough time. Large mammals are especially vulnerable. Elephants, whales, bears, and many other large species produce relatively few young. Even when a useful adaptation appears, it may take centuries for that trait to spread through the population. But temperature is only one part of the problem. As the climate changes, the plants that support entire food chains also change. Plants depend on a specific combination of heat, rainfall, soil conditions, sunlight, and seasonal timing. When these conditions move, vegetation zones move with them. Others are trapped by mountains, cities, farms, deserts, or oceans. To understand how ancient vegetation reacted to extreme warming, scientists also study fossil leaves in Wyoming. Before the PETM, the region supported rich forests. As the world became hotter, those forests changed. Fossils show that plants normally associated with warmer climates appeared in the area. Relatives of palms, mahogany trees, and bean-producing plants moved north. Across the planet, vegetation zones shifted toward the poles. Warm forests grew in places that now experience freezing winters. Many of the fossil leaves from the EPETM contain signs of heavy insect damage. Tiny holes, missing edges, tunnels, and bite marks are preserved in the ancient rock. Researchers discovered that leaves from the hottest period were attacked more heavily than leaves from the cooler periods before and after it. There are several possible explanations. Warm conditions may have allowed insects to reproduce faster. Longer warm seasons may have produced additional generations each year. At the same time, changing vegetation may have forced more insects to feed on fewer available plants. But another explanation is even more concerning. When the amount of carbon dioxide in the atmosphere increases, plants can grow with a higher proportion of carbon in their tissues. However, they may contain less nitrogen and lower concentrations of certain nutrients. Insects need nitrogen to build proteins, enzymes, and genetic material. If each leaf contains less nutrition, an insect must eat more leaves to receive the same amount of food. This could explain why plants suffered greater damage during the ancient warming event. The same issue could affect our future food supply. Human civilization depends on crops, such as wheat, rice, corn, and soybeans. The world population requires enormous quantities of food every year. If rising carbon dioxide reduces the nutritional quality of important crops, producing enough calories may not be the only challenge. Food may also provide fewer essential nutrients. Meanwhile, insects and crop diseases may expand into regions where they were once limited by cold winters. Farmers could face heat, drought, pests, water shortages, and declining soil quality at the same time. The effects of warming can already be seen in modern forests. Across parts of Europe, large areas of trees have died in only a few years. Drought weakens the trees by limiting the water available to their roots. Heat adds further stress. When trees become weak, insects can attack them more easily. Bark beetles are one example. These insects can reproduce rapidly during warm weather. Cold winters once killed many beetles and kept their numbers under control. As winters become milder, more beetles survive. They then spread through forests already damaged by drought. Spruce forests are especially vulnerable in some regions. Spruce trees were often planted because they grow quickly and provide valuable wood. But their roots are relatively shallow. During long dry periods, they cannot reach water stored deep in the ground. Once beetles enter a weakened tree, they can destroy the tissue that moves water and nutrients through the trunk. The tree dies, and the insects move to the next one. Satellite images reveal the scale of the damage. Areas that appeared healthy only a few years earlier can quickly become filled with dead and dying trees. Foresters are now trying to create more resilient landscapes. Instead of planting only one species, they are developing mixed forests. Different trees respond differently to heat, drought, pests, and storms. A diverse forest has a better chance of surviving because one disaster is less likely to kill every tree. Some experts are planting native species that tolerate warmer conditions. Others are carefully introducing trees from regions that already experience the climate expected in the future. But changing a forest is not simple. Trees can live for decades or centuries. A tree planted today may experience a very different climate when it reaches maturity. Foresters must therefore make decisions based not only on the weather of today, but also on the world of 2050, 2080, and beyond. Forests are essential to life on Earth. They provide homes for animals, protect soil from erosion, support rainfall cycles, cool the surrounding air, and store enormous amounts of carbon. Through photosynthesis, trees take carbon dioxide from the atmosphere. They use the carbon to build leaves, branches, trunks, and roots. The oxygen is released into the air. As long as the tree remains alive, much of the carbon stays locked inside it. This is one reason forests help slow global warming. However, forests can only protect the climate while they remain healthy. When trees burn, die, or are cut down, their stored carbon returns to the atmosphere. Ancient rocks from the PETM contain fossil charcoal. This charcoal is the remains of plants burned by fires approximately 56 million years ago. Its presence suggests that wildfires became more common during the ancient warming period. The modern world may be moving in the same direction. Hotter temperatures, dry leaves, grass, and branches. Long droughts remove moisture from the soil. A lightning strike, damaged power line, abandoned campfire, or deliberate act can then ignite the landscape. Once a fire begins, strong winds can push it through forests and towns at terrifying speed. In recent years, enormous wildfires have affected the United States, Canada, Southern Europe, South America, and Australia. Some communities have been forced to evacuate repeatedly. Homes have been destroyed. Air pollution from smoke has traveled hundreds or even thousands of kilometers. People far from the flames have experienced dangerous breathing conditions. Australia's devastating bushfire season showed how destructive such events can become. Forests, covering an enormous area, burned. Billions of animals were killed, injured, or displaced. Some survived the flames, but later died because their food and shelter had disappeared. The fires also released hundreds of millions of tons of carbon dioxide. This creates a dangerous cycle. The additional carbon causes more warming. After fire, green plants may return surprisingly quickly. But a green landscape does not mean the original ecosystem has recovered. Repeated fires can prevent forests from rebuilding at all. A region that once supported tall trees may eventually become open grassland or dry scrub. Scientists are also examining whether forests will continue absorbing carbon as atmospheric carbon dioxide rises. At an experimental eucalyptus forest in Australia, researchers exposed groups of trees to carbon dioxide levels expected in coming decades. Carbon dioxide is used during photosynthesis. More carbon dioxide should allow trees to photosynthesize more. The measurements confirmed part of this expectation. Leaves exposed to higher carbon dioxide became more active. They absorbed more carbon during photosynthesis. The trees were not growing significantly faster. The extra carbon did not remain stored in additional wood. Some of it traveled through the trees into the roots and eventually returned to the atmosphere. The forest had increased its photosynthesis, but its long-term carbon storage had not increased by the same amount. This result challenges an important assumption. Climate models often expect forests to absorb more carbon as carbon dioxide concentrations rise, but trees also require water, nitrogen, phosphorus, and other nutrients. Carbon dioxide alone cannot produce unlimited growth. When another resource is missing, additional carbon may provide little benefit. Scientists fear that this could push the Amazon toward a tipping point. A tipping point is reached when a system changes so much that it cannot easily return to its original condition. Beyond that point, a large section of rainforest could transform into a much drier landscape. Such a change would affect rainfall, farming, wildlife, and climate far beyond South America. Another major tipping system lies in the far north. The Arctic is warming much faster than the global average. One reason is the loss of ice. Bright ice reflects sunlight back into space. Dark ocean water and exposed land absorb more solar energy. When ice melts, more heat is absorbed. That heat melts even more ice. This is another self-reinforcing cycle. Summer sea ice has already declined greatly. Scientists expect that the Arctic Ocean may experience nearly ice-free summer conditions within the coming decades. The disappearance of sea ice will not directly raise sea levels because the ice is already floating. But it will change weather patterns, ocean conditions, wildlife habitats, and the amount of heat absorbed by the planet. Polar bears, seals, walruses, and many other species depend on sea ice. When the ice disappears earlier in spring and returns later in autumn, these animals lose access to feeding and breeding areas. The land surrounding the Arctic contains another danger. Much of the ground in Alaska, Canada, Siberia, and northern Europe is permanently frozen. This ground is called permafrost. Some permafrost has remained frozen for tens of thousands of years. Inside it are huge amounts of ice. ancient roots, dead plants, and animal remains. The frozen soil preserves carbon that was once removed from the atmosphere by living plants. As long as the ground stays frozen, much of that carbon remains trapped. But when permafrost thaws, microbes begin breaking down the ancient organic material. This process releases carbon dioxide and methane. Methane is especially powerful at trapping heat during the decades after it enters the atmosphere. The amount of carbon stored in permafrost is enormous. If only a fraction of it is released, it could make climate change more difficult to control. Once again, a feedback cycle appears. Warming thaws permafrost. Thawing releases greenhouse gases. Those gases create additional warming. Permafrost is already beginning to collapse in some areas. The ground can sink when underground ice melts. Roads bend and crack. Buildings become unstable. Pipelines and other infrastructure are damaged. Forests develop strange leaning trees because the soil beneath their roots is moving. Communities built on frozen ground face growing risks. In some northern cities, houses rise and fall as the soil freezes and thaws. Repairing these structures can be extremely expensive. Moving entire communities would be even more difficult. For the people who live there, the crisis is not only about property. It is also about culture, family, identity, and connection to the land. The Arctic is home to communities that have followed local traditions for generations. Leaving would mean losing far more than a building. Animals living in cold regions face an even greater challenge. A human community may be able to build cooling systems, import food, or move to another location. A species that can survive only in a narrow climate zone may have nowhere to go. As temperatures rise, cold environments move toward the poles and higher into the mountains. But eventually, the land ends. A mountain species can climb only until it reaches the summit. After that, there is no colder habitat available. Australia's mountain pygmy possum is one example. Only a few thousand remain in the wild. They live in high mountain areas where winter snow once provided important protection. Snow acts like a blanket. Although the air above it may be extremely cold, the space beneath a thick snow layer can remain close to 0 degrees Celsius. The possums use this protected environment during winter, but warmer conditions are reducing snowfall. Without enough snow, the animals are exposed to far colder air. They use their stored energy too quickly and may not survive until spring. A few winters with very little snow could be disastrous for the species. Traditional conservation may not be enough. Protecting the existing mountain habitat cannot solve the problem if the climate itself disappears. Researchers are therefore looking into the animal's ancient history. Fossils show that the ancestors of modern mountain pygmy possums once lived in warmer, lowland rainforests. They were not always mountain animals. This discovery has inspired an unusual conservation idea. Scientists may be able to breed a small population in controlled conditions and gradually introduce them into a habitat more similar to the forests occupied by their ancestors. The method has been described as using paleontology for conservation. Instead of looking at fossils only to understand extinction, researchers use them to discover where a threatened species may have lived successfully in the past. The approach is experimental and may not work for every animal. Moving a species can create new ecological problems if it competes with local wildlife or spreads disease. However, in carefully selected cases, it could provide a final option for species whose current habitat is disappearing. The larger lesson is clear. Plants and animals have adapted to climate change before, but ancient adaptation required time. The PETM unfolded over thousands of years. Even then, ecosystems were transformed, species moved, and animals changed in size. Modern warming is happening within the lifespan of individual humans. A child born today may witness changes that once required many generations. Climate zones are already moving. Spring is beginning earlier in many regions. Winters are becoming shorter. Heat waves are lasting longer. Rainfall patterns are changing. Some places are receiving less water, while others experience heavier storms. The stable climate maps, once taught in schools, are becoming less reliable. New climate conditions are appearing in areas that have never experienced them before. Unlike during ancient hothouse periods, more than 8 billion people now depend on a complex global civilization. Cities, farms, roads, ports, power stations, and water systems were built for the climate of the past. A major shift would place all of them under pressure. Extreme heat can make outdoor work dangerous. Drought can reduce crops and drinking water supplies. Floods can destroy homes and spread disease. Sea level rise can damage coastal cities. Wildfires can force entire populations to move. The effects will not be equal. Wealthier regions may be able to build stronger defenses. Poorer communities may have fewer resources to adapt, even though they often produce the least pollution. Climate change could therefore increase inequality, migration, and conflict. Does this mean a hothouse future is unavoidable? No. Earth's climate contains dangerous feedback systems, but the future still depends greatly on human choices. The most important action is to reduce greenhouse gas emissions. That means replacing fossil fuels with cleaner energy, improving efficiency, protecting forests, changing transport systems, reducing methane leaks, and developing better industrial technology. Protecting existing ecosystems is also essential. A healthy forest, wetland, grassland, or mangrove can store carbon and protect communities from extreme weather. But nature cannot carry the entire burden. Planting trees is valuable, yet it cannot replace major reductions in coal, oil, and gas emissions. Adaptation will also be necessary. Cities can create more shade, improve drainage, protect water supplies, and design buildings for extreme heat. Farmers can use more resilient crops and protect soil moisture. Foresters can create mixed forests that are better prepared for drought and insects. Wildlife corridors can help species move towards suitable climates. Scientists can use fossils, genetics, satellites, computer models, and long-term observations to identify the places and species facing the greatest danger. The ancient past does not provide a perfect picture of the future. The continents were in different positions during the PETM. Ocean currents were different. There were no modern cities, industries, farms, or billions of people. But the PTM still delivers a powerful warning. When carbon rises quickly, the planet changes. Temperatures increase, oceans warm. Vegetation moves, wildfires become more common. Food chains are disturbed. Animals are forced to adapt. Some survive by becoming smaller, changing behavior, or moving into new regions. Others disappear. The difference today is that humanity understands what is happening. We can measure greenhouse gases in the atmosphere. We can observe the melting ice. We can track forest loss from space. We can calculate how much carbon is released by energy systems, farming, industry, and deforestation. And we can choose to change direction. The question is no longer whether climate change is real. The evidence is already visible across the planet. The question is how far we will allow it to continue. Will forests remain powerful allies, or will they become sources of carbon? Will the Arctic remain frozen, or will its stored greenhouse gases escape? Will animals receive enough time and space to adapt? Will human communities prepare before disaster arrives? Earth has entered hothouse conditions before. Eventually, natural processes removed carbon from the atmosphere and the planet cooled again. But that recovery took tens of thousands of years. Human civilization cannot simply wait for geological time to solve the problem. For us, the next few decades matter. The rocks of Wyoming, the shrinking Arctic ice, the burning forests, the struggling meerkats, and the endangered mountain possums are all telling different parts of the same story. The climate system is changing, nature is responding, and time is becoming increasingly important. The future has not yet been written, but Earth's past has already shown us what can happen when greenhouse gases rise and the planet loses its balance. We can treat that history as an interesting scientific story, or we can treat it as a warning. The choice we make may determine whether future generations inherit a stable living planet or a world transformed into something humanity has never experienced before.